We're now at this part of the day which is sometimes the most daunting for speakers, the dreaded post-luncheon spot. But I can guarantee you that that is not the case today, because we have a really exciting speaker and presentation, and I have the honor of introducing him. Dan Kammen is a professor at the Energy and Resources Group and the director of the Public Policy, Renewable and Appropriate Energy Laboratory here at the University of California at Berkeley. He has extensive and intensive research interest studies in science and technology policy focused on energy, development, and environmental management. Also on technology and policy questions in developing nations, particularly involving the linkages between energy, health, and the environment. Ruth Coleman, in her introductory remarks, talked about the need in government at the local, regional, state, and federal levels for applied scholarship. And I can tell you now, having been at UC Berkeley for the last year and a half, that Professor Dan Kammen really embodies that. He is fully engaged, in addition to his teaching and research here on campus, in actively consulting with and advising state officials such as the Air Resources Board at the national level, and is a recognized authority globally on climate change issues and the challenges that provides us both on the adaptation and mitigation side. So I'm thrilled to be a colleague of his on the UC Berkeley faculty. I'm thrilled that he's taken time from his busy schedule to visit with us today, and I introduce you to Professor Dan Kammen.
Well, thank you all so much for the chance to do this. There's a couple interesting themes that will sort of tie together what I want to talk about, which is largely our current mix of energy demands and wants and what it does to the environment. But I'm going to highlight a couple things that are going on around us. Quarter mile away on campus, some of my students are currently protesting the deal that Berkeley signed in the last 24 hours with BP for this $500 million biofuel research institute. And some of my other students are research assistants on that same project. So that's typical Berkeley, but in a good sense. And I'm going to come back to that a number of times, because for all of the energy demand questions out there, it's not just that the whole biofuel question relates to land use and land management in a number of very, very obvious and direct ways. But I actually think it's a harbinger of things that are going to come, both good and bad. And so what I'm going to try to do over the next 30 minutes is highlight a number of those. And I'd like to do one thing that I didn't actually clear with the boss, and that is, if you have a question that pertains to one of the pieces of either technology or policy that I mentioned, and it's not a big discursive one, like nuclear power, where the hell is it in this mix? I'd actually rather you just ask as we go. And I will say to some of them, let's wait till the end. But there are some that are sort of the context. What does solar do to land use, et cetera? So if you have one that really seems like it's germane at that moment, or if I used any energy buzzwords, just give a holler, and we'll sort of take some of them as we go through. Whoops, I may need your help. Okay, never mind, got it, okay. I'm going to start with the big picture in terms of what California has just done on climate change issues. And I'm going to also tie this to why California's Assembly Bill 32, that I assume everyone has heard of in one of the various forms. This is the Pavley-Nunez bill passed in September last year, is going to be transformative, not just for California, but for the whole western part of the country, and by extension, a number of states and cities and the countries doing like-minded things. So I'm going to spend a few minutes on this slide just to really highlight the setup. What AB 32 does is to, first of all, recognize that California and the US ignored the Kyoto Protocol, did not take action, because what this does is it calls for our greenhouse gas emissions, instead of continuing at their business as usual or business as disgustingly dirty path has been, and essentially says over the next 2 decades, we need to bring our emissions levels back down to our 1990 baseline. That is a remarkable thing to say, and those of you who have met and interacted with Assemblywoman Fran Pavley, Fabian Nunez, the governor, there's been a lot of people who put effort into doing this, and there have been some interesting and complicated compromises along the way, and some of you have played a pretty key role in doing it. But what I want to highlight are two things about this. One is that California has called for us to do something that we, in theory, know how to do, cut emissions by 25%, but no one in history has ever done this if it wasn't for some other reason, i.e. France can claim that we've cut our emissions by 80%. That was because France made a policy choice unrelated to climate change to go nuclear. Iceland did it because they sit on a huge repository. California, if they do it, will be doing it not because it was the convenient politically or economic solution. It's because it was a measured decision to not only cut emissions back down to 1990 levels over the next 2 decades, but also to engage in a process to bring emissions down to 80% below this baseline by 2050. And anyone who views getting AB 32 done as a big task would be correct. But anyone who views getting this done as a big task and as an endpoint would be dead wrong. Because if we only do this, all it really means is that we cook a little slower. If we can get on a path to do this 25% or so now, and then by 2050 down here, an 80% cut, that's the path we need to be on. And so policies need to be long range, and technology strategies need to be long range, and no one has done this. And of course, everything we're talking about are great words. We are still, by the way, on this increasing path. So great language, great stuff to start with, but zero demonstrable action. Lots of good things being passed, but our emissions trajectory has not yet turned over, and that's the hardest step in the process. And I'm dwelling on this because what's going to come out of this decision-making process are features of state policy and regional policy and decisions by companies, cities, et cetera, that are going to have tremendously broad land use impacts. And while work in my lab and many others concludes that in time, we have a chance to do this whole transformation from being a carbon-intensive economy, i.e. one where we have essentially robbed from nature, from fossil fuels to get this far, to one where we actually have a sustainable economy to some extent. This is a process that our analysis is will build jobs, will not cut jobs in net over the coming decades. But don't be mistaken, in the short term, there will be some major dislocations. So this is not going to be a pain-free process. And as we all know, not pain-free in California means incredibly complicated and intricate deals will be struck in process, and we have to think about that. Part of the initial motivation for thinking about climate change was, of course, we want to reduce the amount of damage we're doing to the planet, but at the same time, we also critically need to reduce our dependence on foreign oil. And many of the current policies being discussed are really about how we can substitute foreign oil from countries that we're now saying are bad in some sense to other sources. And those energy security arguments actually can make our climate change job worse. This is an open mine, as anyone can tell. This is actually not a coal mine. This is a tar sands pit in Alberta. In Alberta, the soil is about 10% or 5 to 10% oil by weight, and it's in a solid form. It's the consistency of a hockey puck, so it's very appealing in Canada, the Prime Minister. You see this stuff up at the top, this green stuff here? That's actually called the overburden. It's not called the ecosystem, it's called the overburden. You have to get rid of that to get what's down here. And the reason why I'm highlighting this is because getting this basically solid tar into a gasoline form costs a lot of energy. And this stuff is mixed with lots of impurities, one of which is sulfur that you'll see in a second. The issue is that there's more oil in the ground in Alberta alone than in Saudi Arabia. And so if a switch to energy security means dealing with those much more friendly Canadians, although Albertans aren't that friendly on the energy front. Any Canadians in the room? So I'm from Ithaca, New York. I'm a Southern Canadian. No Canadians here. That's interesting. Okay. So any of you who know, Alberta as a province made $20 billion last year because the oil and gas industry is doing so well. And in Canada, you don't have to share. So Alberta keeps what Alberta makes. And so there are some complications, but it also means that the policies, when you're making 20 billion as a province, are hard to change. There's more oil here than there is in Saudi Arabia. And if we ever got done burning through this stuff, there is as much oil in this solid form in Venezuela, in this tar sands form. And there's as much oil in the form of rock in Utah and Montana, in shale, as there is in these locations. Translation, all of the neat stories about peak oil are false. It is true that there's a shortage of the easy-to-get cheap stuff, but there's lots of fossil fuel out there, and if part of our policies direct us to being more energy secure, well, Alberta, even though they're a little far away, is pretty convenient. And so we have a real large likelihood to make our job much worse unless things like California's policies, that I'll detail in a second, get put in force in land use decisions, in decisions by companies, in decisions by cities, in industrial policy. This is not going to be easy. I mentioned the sulfur. There's so much sulfur coming out of the ground here that they're producing huge pyramids of sulfur because the world market for sulfur is flooded. This is very far north in Alberta. That's not a lake, that's a settling pond. So they're doing 1 million barrels of oil a day from Alberta. The largest oil field on earth, the Ghawar field in Saudi Arabia, is doing under 5 million barrels of oil a day. And the forecast that Alberta made 3 years ago was they wouldn't get to 1 million barrels of oil from tar sands until around 2013 or 14. So this is accelerating very fast, and these are big piles of sulfur. And sulfur is a minor pollutant in the fraction of tar sands in the soil. So there's a huge amount of issues and waste out there. California is not the only place whose emissions are increasing. This is the federal emissions. I've jumped up in scale. California is about 2.5% of the U.S. greenhouse gas emissions. And the federal trend is depressingly increasing just as the California one is. And our path is higher and higher. And by the way, the U.S. is about 25% of the world's greenhouse gas emissions. Our policies have been to skip the Kyoto Protocol and just ignore it. The administration has a very bizarre piece of inability to do mathematics. It turns out that we do have a federal greenhouse gas policy, but it's not based around the amount that you emit. It's based on how clean each dollar of GNP is. And that's the most bizarre misunderstanding of a stock and a flow I've ever seen. And so I'll just leave that to our lack of science education in the White House. This is California's policy if President Schwarzenegger were in charge. I've taken the AB 32 and scaled it up to the size of the nation. So I've multiplied by about 8.5 to go from the California mix to the overall US one, to highlight where California is committed to passing through these boxes. That's AB 32, and this is our long-term goal. And the ways that we hope to get there are through a variety of policies and technologies I want to talk about at a little bit of length now. Now, some people are saying that the US shouldn't go it alone until China and India sign on to climate policies. And some other people are saying California shouldn't go it alone because Washington is going in another direction. But I want to highlight that that's really false. And people who hide behind that excuse, and there are many, are missing a number of critical stages. The frustration with federal greenhouse gas policy, and anyone who's been to Europe recently knows that you cannot watch the news, read any paper, go to any town hall meeting without seeing huge amounts of discussion about climate change and what will actually be done. Know that what I'm going to describe now is really much more the norm overseas than it is here, and it is being put into practice. The states colored in red, and I've actually made a mistake. Since I made the slide, it's now 29 states. All the states listed in red are states that have committed to having a fraction of their electricity, and a significant fraction, coming from renewables, zero and low carbon sources, by different dates. California has one of the most aggressive ones. I didn't intentionally hide it over. California is committed to 20% of our electricity from renewables by 2010. And the working policy framework is actually to be going for 33% by 2020. Some other states are quite aggressive as well. New York has a standard which is very aggressive. We differ between California and New York on whether you should count large hydro in this mix or not. But these states are not only committing to standards at different levels, but they're also states that are likely buyers for the technologies that California is likely to produce. 40% of all venture capital money in this country flowing into the energy area, which has now overtaken computer technology in terms of the lead area of venture capital funding, is in Silicon Valley. So California is a driver of these companies, and if we can drive them to be formed but not send them out of state, we will actually also capture a large number of jobs from this process. And these states now, and an increasing set of them eventually, are all markets for this. So the idea that California is going to do this and is incredibly exposed and will commit to these standards and is going to go bankrupt because of this is false. Now, anyone who read the paper today and notes that California has a minor little $10 billion structural defect, which some of our state senators and others have worked on, is a real issue. But dealing with climate change is more likely to bring jobs and bring revenue to the state than to cost us. And it may actually be a very large winner. And in fact, I just came from a meeting this morning with the mayor of Shanghai, who is working to set up partnerships with the western US states on climate issues. And in fact, China, not the US, boasts the first billionaire based on clean energy. We don't yet have one. A friend of mine would like to make his next billion in clean energy, which is Richard Branson, but he's making his first billions on records and then airplanes. But there's an entrepreneur in China who is now a billionaire through solar, and it's the first such sort of charismatic megafauna of the clean future, if you will. So this is, in fact, our market. And the state that began this process was Texas, under then Governor Bush, who noted that wind power from this part of the state is half as expensive as natural gas. And I just testified in Washington, D.C., and a certain Republican congressman from California, who I won't mention, Darrell Issa, challenged me that wind is a bad deal anywhere because you can't build wind for less than about 8 or 9 cents a kilowatt hour. And in fact, in a great deal of this part of the country, wind is not only the fastest growing new source, but it's the cheapest by often a factor of 2. What we do not have in this country, however, to bring all that wind to market are policies to build the transmission lines to what we're going to need. And any of you who have dealt with any of the CEQA issues around land use know that transmission lines is incredibly difficult. I see several, you're grinning, which is strange because my dealings with CEQA have not been smiles always. This is a process that we are going to have to find a way to deal with and not just hope permitting goes faster. We're going to have to find a way to benefit clean power, and that takes infrastructure. We built much of our railroads to benefit coal in this country. We are going to have to find a way to do this for clean power. And even within that mix of states that have these renewable energy obligations, these sets of states give extra benefits to the currently most expensive technology, which is photovoltaics. And I'm not going to get into, because I don't have time, the very complicated ways that while the price for power that most of us pay is between 12 and 14 cents per kilowatt hour, and photovoltaics is, quote unquote, much worse because it's about 25 cents. And who has solar on the rooftop here? That's pretty good. You guys are actually much better than the average, even Berkeley audience. I'm impressed with that. The financing of solar is not one for which there's a simple answer. If your view on economics is pure 1880, solar costs 25 cents. If your view of economics is a little more progressive, solar is cheaper. And if your view of economics is what's taking over in Berkeley and Oakland and San Francisco, which I'll describe in a few minutes, solar is in fact close to on par with the price of fossil fuels. Now, that takes some complicated financing, and I'll get to that in a little bit. But I do want to stress that for new technologies that don't look like big fossil fuel power plants with grandfathered power lines and leases and all manner of things, renewables are not, in fact, always more expensive. And in fact, wind in the good sites is cheaper, and the best piece of land on Earth for wind is this part of the country right here. California has an excellent wind resource, but it largely blows at night. And I'll talk a little bit about ways to capture that later on. I'll talk about biofuels, and just to note that the incredible run-up in interest in biofuels naturally follows this incredible run-up in the price of oil. And at one level, this should really worry you, because what you're essentially saying is that the low efficiency of growing crops, even if we engineer them and all kinds of great stuff, we're asking land, be it US land or land in Brazil or Africa, to subsidize our driving of SUVs. That's a bad trade-off on every single axis. And right now, if you take corn and make it into ethanol, you receive a 50-cent per gallon subsidy, which is massively distorting. And if you're in Brazil, where the climate actually favors sugarcane and ethanol, which is 8 times as productive in terms of ethanol per area, you receive a 51-cent per gallon penalty. So there's a $1 subsidy in place subsidizing a crop that we have a lot of, which is a terrible biofuel, relative to one that's a good biofuel. And California, for all its good policies, has not actually removed the subsidies that exist for making a foodstuff, a very poor biofuel, into ethanol. Now, that being said, corn into ethanol, if the distillery that makes it is clean, i.e. it's wind power or natural gas, is not awful. It's not a winner. It's 10 to 15% better than it's using the gasoline directly. And perhaps it can help us transition to the so-called cellulosic types of ethanols. But it is not something to build a policy around. And yet right now our president is building a policy around supporting this stuff because it's a convenient way to subsidize farmers. Not a good energy policy. So we've got some major barriers to get at. So we've done a lot of work on this. There's a model of ours that has been widely used. I won't dwell on the model details, and I'm actually not going to dwell. I've sort of highlighted the fact that if we don't do our biofuels right, the orangutan gets it, i.e. gets shot. I am going to highlight the degree to which one of the opportunities for biofuels and for clean energy is that we might actually get competition over how you fuel your car up. And that's something that we have not had in this area for a long time, i.e. you could put gasoline into the car, you could put corn ethanol in, if you don't listen to me, you could put in cellulosic ethanol, which we do not have much yet, but we expect to have in the emerging years, or you could charge up your car with electricity from the grid. Now, the grid in California is very clean relative to the US overall. If you drive a car with a lot of batteries in the back, a plug-in hybrid, off of electricity in California, it's much cleaner than using gasoline. In fact, it's equivalent to driving at around 80 to 120 miles per gallon. If you airlift that same car to West Virginia, a very coal-intensive state, and you then drive that car there, it's much worse. So policies are going to matter regionally. I'm going to highlight this story with the following one, which I've sort of explained, and that is that on a greenhouse gas basis, this is pounds of CO2 emitted per gallon of gasoline. If gasoline is your benchmark, the things I mentioned at the beginning, tar sands, making coal into gasoline, which we know how to do, by the way, these are significantly worse than even gasoline. And there's a gradation of cleaner fuels that we could use that go towards biofuels and even towards these plug-in hybrids. So California, the governor did something incredibly courageous. The governor said our baseline, our current ugliness of our liquid fuels, how greenhouse gas intensive it is our baseline in 2007. And he committed the state to reducing that number by 10% by 2020 or more. So the governor actually was very courageous. He signed this to the point that our spreadsheets were not even quite hot off the presses. We thought we could go further than this, but the executive order that was signed says, make our liquid fuels 10% cleaner over the coming 13 years, and more if we can. And you'll notice what it says is that this is a policy that discourages these, but doesn't absolutely forbid them. If you really want to make coal into gasoline, which is happening around the world right now, you're going to have to offset that with a tremendous amount of this stuff. And the goal in California is to ratchet this standard down enough that these things are excluded. And a lurking item that we'll talk about at the end is the degree to which a carbon tax or a cap and trade system, either mechanism will come into play under AB 32. Those mechanisms increase the price of all these and give all these a credit they could sell back into the market and further tip us towards this cleaner mix. So there's some very critical aspects of this process that we could do. And in fact, there are biofuels out there that do not take land at all. There are ways to, for example, grow algae in tanks and use the CO2 waste that comes out of a power plant and use that as the feedstuff for your bugs to grow algae that can be made into biofuels. So there are some dramatic options that we hope in this big BP with Berkeley deal to research, and a number of other universities around the country are working on similar topics. So if we continue to push on the R&D side, easy to ignore because federally we don't invest in R&D, and California with a budget crunch is going to have even more of an issue here. Continuing to invest in making algae into biofuels, making municipal waste into biofuels, and finding ways not to make corn into biofuels, but to actually help to replenish prairie land by harvesting after the growing season a ecologically sustainable, diverse mixture, is another technology being worked at by researchers at Berkeley, at University of Minnesota, et cetera. These are all things that we think we know how to do now, but do not really know how to fully put together, and that's the next challenge in this process. Let me highlight how important that push on technology is going to be for all of the land use questions we're talking about. I've just highlighted total land area required to meet all US on-road vehicles, so I'm leaving out railroads and things, but all liquid fuels used by our light and duty trucks, and two highlighted numbers. This is total US cropland, and that's the Conservation Resource Program. And if we produced ethanol to replace our gasoline addiction, and we did it with the current efficiency of growing biofuels and of converting them into liquid fuels, we would need more land area than the US has in total, which is a problem. If, however, we push in terms of making the processing of the fuels better, not growing more efficient fuels or growing more, but the processing advantages that much of our chemical engineering community thinks is possible over the next, say, 5 to 10 years, we could actually reduce our demand to be that of all US cropland. Better, but still kind of a problem. If we also combine that with doing something we've ignored for the last 30 years, which is making our vehicles more efficient, the so-called CAFE standards, we start to get down to more manageable numbers. Notice that this is a target that every analyst thinks is possible, and every analyst who has argued for it knows we've done nothing about over the past 30 years. So it's a possible, but not a done so far. If we increase the yields of biofuels by about the 2 to 2.5, that would be the equivalent of not inventing some super crop, but of actually making our biofuel crop as efficient as sugarcane is. Now, we wouldn't grow sugarcane because that's not a temperate zone crop that we'd want to grow much here, even though there are a few places that are trying it in a bizarre experiment. But there are other crops that have actually even higher yields. One is miscanthus. It's a Chinese switchgrass. There are a number of these things. Now we start to talk about a land area, if combined with these other innovations, that actually makes the ability to totally meet our liquid fuel needs. I'm not talking about 10%. I'm talking about meeting it all from biofuels as a possibility. And I'm not quite so naive as to think that we're going to switch from gasoline to just a biofuel mix. What I see is a mix of fossil fuels in there, buying some credits to offset those fuels, and then using our nighttime electricity from excess wind or nuclear or other things. Oh, sorry, yes?
Have you taken a look at water requirements?
Yeah, we'll talk about it briefly in the Q&A. And the question is, if you grow crops the way we grow corn, we might as well just divert the whole Colorado River to doing this operation. Many of the processes that use cellulosic crops do not, in fact, require irrigation. And so the ability to bring the water use on the growth side dramatically down is there. We have not brought down the potential need for water in the actual distilling process. And so there's much R&D room to be done. And then there is a variety of strategies to multi-crop and to mix in our solid waste that could probably produce 10% of our total liquid needs, et cetera. What I'm highlighting is that if we continue to invest in R&D, biofuel is not, in fact, necessarily a trade-off between growing crops either here in developing countries or fueling your vehicles. We would have to make the vehicles better, i.e. the SUV has got to go. We have options to mix these with other technologies, and this is really a mix of things that we actually could get done. Now, I'm going to leave that one for now. It's the most direct one. I'm going to highlight one last feature and then actually stop, and that is that one of the things that's come about, and sort of something I would like to challenge this group to do, is the old, wizened energy thinkers like myself, those who've done this for a long time, are not the only source of innovation in this area. The city of Berkeley, a manager of property tax issues, noticed that many US cities currently do something that, if applied to clean energy, transforms the equation. Right now, if you want to buy solar, it is equivalent, as those of you who know have done it, unless you happen to have a home equity loan that you're going to use, it's like buying your next 20 years of cell phone minutes in advance. That's a bad plan. And I know my daughters would not have cell phones if that was the case. But we require us to buy clean energy that way because they're capital intensive with low or no fuel costs. Berkeley noticed that, in fact, all the time they allow residents to borrow city money through an assessment district for things like undergrounding power lines or fixing piping, et cetera. And what you do is the city pays for it up front, and you pay back on property taxes. Berkeley noticed there's no reason not to apply that to energy efficiency. Always the best investment in new energy is efficiency, and then allow you to do to fund solar this way, so that suddenly there's no upfront cost. The bill for solar goes onto your property taxes. It's paid off over 20 years. You then pass it on to the next owner if you sell the home, and it transforms what was the most expensive way to buy power to actually one of the cheapest. This is so exciting, and literally this came from someone with no particular energy background, a very smart guy, but no particular background, to a plan that the day before it had been released, we have not even figured out all the tax issues within the city of Berkeley. The Attorney General wants it to go statewide, and I've never received a call from the Secretary of Energy before in Washington. I got a midnight call his time saying, how can DOE help? And they have this wonderful little logo, the Solar America City, of which San Francisco and Berkeley are examples. So what I'm highlighting is the opportunities for innovation come from a whole range of things, not just from the traditional energy assessments, because many of the things that we've been thinking of for many years are now in play, but all of the innovative land use strategies, right-of-way issues, financing things are going to have to come from a new wave of thinkers on this. Thank you very much, and we can do questions until the time is up. Yeah.
Frank Jordan from the Gordon and Betty Moore Foundation. Can you give us some idea of your thoughts about the possibility of tidal power as an alternative energy source?
Yeah, so great question, and Berkeley, San Francisco is one of the centers of this. As you know, under the Golden Gate Bridge, there's a plan now to put an experimental system. Tidal power that was sort of left for dead for a long time because no one wanted to see big sort of floating things like this along the surface to get the energy from them bobbing up and down. I shouldn't spill water onto the computer. Or to have sort of inline turbines underwater on the surface, were thought of as cute, sort of potential small-scale applications, largely until a series of R&D efforts by the Europeans. There's a UK and a EU Marine Research Center that are working very hard on this, and now this looks much more promising. The issue in this case is going to be places to deploy where you have really good tidal movement, like under the Golden Gate Bridge, and as you think about more surface installations, what are going to be the issues on wildlife and fish? And so this is one of those things that, again, was left for dead, is now back on the agenda, and the degree to which we can manage policies that integrate land use, marine use issues will actually make this one a fairly significant player. And interestingly enough, 5 years ago, the estimated cost for tidal power put it at astronomically high. It now looks like this is one that could become competitive quite soon, but we're going to need to get some of these initial deployments out. So it's very promising, and it's really only reemerged in the last 2 or 3 years on the energy agenda.
It's on? Okay. This is Elizabeth Goldstein. I'm from the California State Parks Foundation, and we, with Linda Carson, who is somewhere in the room, from the Anza Borrego Foundation, are currently engaged in a really nasty fight on behalf of state parks regarding a transmission line going through Anza Borrego, the largest state park anywhere in the continental United States. So, You know
Yep.
what I'm going to ask you. I'm going to
sure
ask
do.
you about transmission. And I guess I'm very concerned that we end up, because SDG&E in that particular case, I don't know whether it's true or not, is claiming that the reason they need these transmission lines to go through Anza Borrego is because they're going to bring renewables to San Diego. So the question is, how do we prevent renewables and energy needs in California in particular from destroying our state park system?
Yep. There is no easy answer to this one. And the issue is that we are going to need new transmission. That particular line looks a little dubious to me. We've looked at it in a little bit of detail, not because we don't need it, but because there's probably a better path through the Las Vegas corridor that we could probably use instead. Not an easy one at any point, because these individual battles don't get fought by kind of a macro energy planner looking at the least cost renewable resources and guaranteeing that's what it get used for. That Anza Borrego line could also bring added coal power in from other parts too. And so if you benefit renewables, i.e. if your loading order, your purchase order dictates clean first, that's a mechanism that we can use to bias it towards renewables. That doesn't solve the fight of going through the park. And these issues are going to come up. And unfortunately, we are going to need some new capacity, largely because the transmission grid we have now is not only old, but it's also designed to go to the places where fossil fuel and hydro resources were. The new resources we're going to have to bring online, or we can really kiss the whole story goodbye, is going to require new transmission. And that's almost impossible to build in all kinds of places. So this battle is going to have to be one where some promise of clean power is going to be weighted against the ecological issues. And this is not going to be an easy one. I'm not claiming there's any solution for it. But you've got to recognize that our grid is hopelessly out of date to bring green power en masse online, because we're not going to solve all of it with just rooftop solar. So this is going to be one of those battlegrounds, and it does pit essentially former allies in some way. We're going to have to find a way to make that work, and it's going to be difficult.
Hi, Stanley Young, Air Resources Board. You mentioned California has wind power in the evenings and at night. Anything hopeful to tell us about storage?
Yes. The hope is that batteries finally are beginning to evolve again. We've had a long period of stagnancy in terms of what batteries can do. So finally we're starting to get not only batteries better, and a whole range of battery startups have happened, but we're also getting other forms of storage. There's ways to store energy by compressing air underground. There's so-called ultracapacitors and flywheels. There's a variety of things. California happens to be very privileged here because we do have a pumped hydro resource. So we have an effective battery system that we can use, but much of the other country cannot. The rest of the country cannot. And so we will hopefully use a fair amount of that as a stopgap until we do get these advanced storage technologies in place. And let me give you a highlight for how important that can be. The price of electricity at 4 in the morning can fall effectively to zero, a few cents to zero, because the demand is low and many stations can't turn off. The price of power on a hot afternoon can be 30, 40, or more cents a kilowatt hour. So if you have enough storage not to last weeks or months, but to last 12 hours, you can make some of these off-peak renewables like wind, but notice also things like letting your hydro down during the day, i.e. pumping it up at night and bringing it down during the day, and nuclear become incredibly good deals. And California right now, new nuclear is illegal, and there's no question there's going to be a large discussion about this, because in exactly the same way that one piece of AB 32 was for California to finally get honest about the fact that we like to say we don't burn coal in state. We burn lots of coal. We just burn it out of state and bring the power in, which is cheating, I would argue. There are plans now afoot to build out-of-state nuclear and bring that into California. And so we're going to have to figure out how does that fit in the story as well. It will displease some of you, but my calculus on nuclear versus climate change would be nuclear.
One more.
Hey, Daniel Press, Environmental Studies, UC Santa Cruz. Hi, Dan.
Hey, Dan.
The land managers at this symposium are really facing mostly adaptation strategies. As habitats shift, either in elevation or in some other way, they're going to have to find ways to to cope with that. So kind of riffing off your last slide, you were talking about a local land use innovation. And I wonder if you might speculate on the kinds of local, or not just local, but maybe state and federal land policy innovations that we might need in order to make that sort of adaptation possible. It's not easy to do a transferable development right between a piece of federal land and a piece of private land. But is that the sort of thing we're going to need to have happen?
I actually think we are, and I mean, this is a great question, and this raises a whole bunch of the issues similar to the transmission line question that I get asked before. Federal lands have a remarkable range of both biofuel resources that we extract the biomass anyway, and wind resources, as well as solar. And so an integrated strategy here is going to have to be one where we get back a little bit to what California used to do in the biannual energy planning process, where we thought through trade-offs between these issues. That's something that we got away from that's now being revised. But if we really want to make best economic, ecological, and carbon choices, we're going to have to build the mechanisms to make that happen. So the example of the solar rooftops, the Berkeley plan, is one where those types of innovations, not in a land use sense, except for our rooftops, is coming back into play. And so, for example, the most important issue in terms of this property, this assessment district, is can you get the interest you pay on your federal taxes tax exempt in this process? Can that be a deduction that you would take? That's something that right now looks dodgy. It looks like we're going to push ahead as if it's possible, but it's something where the Department of Energy, in a sort of a rare move, in my opinion, the Federal Department of Energy, has said they will work with us and the Treasury to make those things go, to make that kind of process go. And if there's ways to off-take biomass from federal lands that would be that would be gotten rid of without making energy out of it, that's one of the example areas where those linkages are possible. And we're going to have to work on those. And again, those are going to in some ways pit former green colleagues around different issue, local ecological versus carbon. But those are the debates we're going to need to have, and we're going to need to export those best lessons. A friend of mine, a colleague at Berkeley, Harrison Fraker, the now stepping down dean of the College of Design, is working on eco-blocks in China. And China is building gated communities, these 50 to 60,000 person gated communities at an amazing rate. What the design team at Berkeley and with an international group called Arup, an architectural design firm, is doing, is to rebuild the model of those. And that model involves land use change, and it involves as much self-generation of power on the buildings, on the rooftops, using the waste into the local power. And those are things that we right now discourage by balkanizing many of the agencies. And you can't deal with this problem unless you think about your water and your energy and your waste at the same time. And again, as all of us in the room know, those types of hoped-for coordination are in some sense the hardest feature of this whole process, but they're going to happen.
Okay, I think that's a good note on which to end. Please join me in thanking Professor Dan Kammen. We're going to proceed directly into the afternoon panels, and to bring us home, I give you the inimitable Rick Rayburn.
All right, thank you. When Sam Schuchat was speaking, he mentioned a clearinghouse for information on sea level rise, and then there was a question later emphasizing the clearinghouse. If you all stick around till 5 o'clock today, you're going to hear about a great tool that's going to be made available to all of you, hopefully for at least the next 10 years in relationship to a clearinghouse related to climate change and conservation research. So stick around for that. Our next speaker is Craig Moritz. Craig is the director of the Museum of Vertebrate Zoology on the Berkeley campus. He's a professor of integrated biology. He was elected a few years ago to the California Academy of Sciences and has been involved the last 3 years in some very interesting research related to identifying evolutionary hotspots on the California landscape to improve our conservation program in terms of protection of not only great places, habitat types, but also processes that allow species to adapt to current existing conditions. And it's just a natural that this research would fold right into climate change and what we can do in the future with those hotspots. So, Craig.
Thank you very much for the invitation to come along. Dan's a very hard act to follow. We're doing a substantial shift now back to the biology that I know and love. But of course it all has to be looked at in the context of the sort of policy shifts in economics that Dan was talking about. So I want to do two things today. I want to talk about dynamics of biological diversity over longer time scales, focusing on the evolutionary process itself, that being the process that drives diversification, that creates diversity, spreads it around the landscape, and gives us what we have to work with now and will so again in the future. And then I want to segue from that into some work we've been doing recently, looking at changes in distributions of birds and mammals over the last 100 years, that is in response to the climate change that has already happened. And I guess if there's a general theme, it is that to predict the future we have to understand the past. Now that's not rocket science. Any economist knows it, any social scientist knows it, any politician knows it. So much of what we're doing at the moment are projections into the future that are largely untested by reference to the past. So I'm going to take us a little bit backwards and look somewhat at the past. So in the broad sense, California is and has been for many decades now, a terrific laboratory of evolution. What does that do? That's scary. Help. Oh, I see. There you go. So many evolutionary biologists over the last few decades have used California as a natural laboratory because it has this extraordinary environmental and topographic diversity across which the plants, the vertebrates and the insects have diversified in the past. And many of our current major concepts in evolution were born from science done in California on this terrific landscape and biota. So our next challenge then is to understand, has this driven specific places in the landscape that have unusual properties that drive diversification? What can we do to protect those? Let me just make this go away. Go away. Help. I'm a professor. I don't know how to do this stuff. What have I done?
Okay, there we are.
You're marvellous.
So, this goes forward.
Oh, the big button that says forward. Excellent. So we want to find out where on the landscape are these hotspots of diversification, and then are these likely to persist? Are these sort of environmental features that drive diversification still going to be there with future climate change? And what land protection strategy might minimise the loss of these sort of landscapes or maximise their resilience? So some months ago, a couple of years ago now, Rick came to us, a bunch of evolutionary biologists, rat catchers, lizard chasers, bird watchers, botanists, and said, right, you've been talking about evolution and conservation, now do it. And we thought, oh my goodness, how on earth do we go about doing this? And it was very exciting as an academic exercise, but also to try and respond to a policy-driven challenge. And that is, if there is to be, and there will be, an active process of land acquisition by the state, by NGOs, land trusts, and so on, how can they invest their money in a way that will maximise the future evolutionary potential of California and maximise its resilience in the face of escalating global change? That's a terrific challenge, and one that we've really enjoyed working on. Now, it's not a totally new concept, this idea of trying to protect landscapes as dynamic entities and to protect not just the pattern of diversity, the current distribution of species, vegetation types, but to protect the ecological and evolutionary dynamics that have created that diversity and will continue to change it. The South Africans are way ahead of us. Richard Cowling and other people there in the state government have been looking at their protected area landscape and trying to think about effects of both future climate change, but also how to maximise protection of the evolutionary processes that made South Africa, like California, a global hotspot of diversity. So they look at things with respect to plant diversification, like steep climatic gradients, gradients in soil types, all the things that are very familiar, particularly to botanists working in California, that shape the current pattern of diversity. So how can we come up with a landscape system based largely on linkages across environmental gradients that would achieve those aims? And my understanding is that this is now having a very tangible influence on the conservation planning policy and land acquisition in South Africa. Now, a lot of these concepts aren't new. They've been mentioned several times today. Protect linkages, protect gradients. And I'll come back to that again and again. So our challenge then was to, this is a very busy slide, don't worry about the detail. The challenge was to look across the California landscape and say, well, can we use existing data, not new data, but existing data, and identify where in the landscape are these hotspots of diversification? Or to put it simply, where do we have concentrations of young species that have evolved in the past few thousands, tens of thousands of years? So to do that, we've focused so far on mammals and amphibians, and there's a project underway on plants as well. Other groups, particularly down in San Diego, are working on invertebrates, and we hope eventually to bring it together. But the notion was to take what we know about the geographic ranges of species, and for this purpose we produced much higher resolution maps than I normally used, based on the specimens we hold in museums and herbaria, and high-resolution modelling methods. So you can take the endemic species in California, which we focused on. For mammals, there's just 26, 130 subspecies, produce these sort of high-resolution range maps, and then connect them to existing information on DNA sequence-based phylogenies, and ask for each endemic species, where does it occur, how different is it in evolutionary terms and in time from its most closely related species. So we're using phylogenies, distributions, and putting them together, and looking for areas where we're getting sort of coinciding young species on the landscape. And then think about what are the landscape attributes that are generating that diversity. So I'm just going to take you through some of the results in sort of cartoon fashion, but there is a lot of data cleaning and data analysis that underlies the pretty maps that I'll show you. So this is the result of the analysis for the mammals, and obviously you know the state. We've also shown some of the federal and state protected areas, or at least federal lands, public lands around the state. The red areas on the map are the areas that are concentrations of subspecies, which are sort of packets of adaptive variation, if you like, on the landscape, in crude terms. And the yellow are the areas that are concentrations of very young species across the landscape. And in several places they coincide. So particularly on the central coast, we're getting coincident distributions of very young species and also phenotypic variation, that is, variation in sort of morphology and phenotype that natural selection has produced. Likewise, in the Central Sierra, through the Tehachapis, turns out to be a very important area, and the transverse ranges and bits of the peninsula ranges. So although there are endemic species distributed well around the state, these are the areas that, from just the perspective of the mammals alone, seem to have the landscape sort of driven recent diversification. That is our evolutionary hotspots. And the point I'll come to later is many of these areas do offer great potential for, through coordinated land acquisition, to protect these sorts of gradients. Some are much more difficult, like the Santa Cruz Ranges and the Santa Lucia Ranges. There's terrific opportunity here that many of you in this room know about and are working on. Some areas, like the Central Sierra, are already well encompassed by public lands. So if we turn to the amphibian diversity, something quite remarkable has happened in the last few years. California now has 40 plus endemic species of amphibians and counting. And about half of these are in this one group of slender salamanders. These are the little pencil-like salamanders you'll find under rubbish lying around in your garden if you live in a wet place. They're really common. It used to be 2 species, it's now 20 and counting. This is the work of one of my colleagues, David Wake, and his students. And this isn't taxonomist splitting hairs. It just turns, or splitting salamanders, or whatever. These things actually look like hairs, just big fat hairs. But in fact, if you look at them closely and study their DNA and their proteins and their distributions, you really do find that there's much more diversity than anyone realized. And in fact, I think this is the map that got Rick Rayburn going on this in the first place, when you look down in the southern Sierra and you've got all these species with tiny little ranges. Many of these are very ancient lineages, just sitting down in areas that are protected from drying out and have remained wet enough for these lungless salamanders to survive in. So tremendous narrow range endemism, that is species with very, very small distributions. And it's not unique here, there's new ones turning up, again on the south central coast, and other little sort of topographic patches through here in other areas. Whereas the north of the state has basically one widespread thing, in the south there's tremendous local diversification. Similar patterns are turning up for some of the invertebrates as well, and Andy Bahonak and others are here who do more of that sort of work. So again, if we sort of massage the data, take the distributions, the phylogenies, and put the story together, it looks something like this. For amphibians, this endemism richness map really highlights the endemic species, the unique species to California that have very small geographic ranges. So here you see the Batrachoseps effect, the southern Californian things. There's a bufo here, there's another salamander up here. But again, the central coast, the sort of central Sierras and foothills and peninsular ranges come up as important areas. And again, with the neo-endemism, the pattern's more complex, but I'll go straight to the comparison with mammals. And there are certain features that are turning up again and again in these independent groups. So again, the south central coast, the central Sierra as a region, and then various regions through the transverse peninsular ranges seem to be important for both taxonomic groups. And this just highlights, if you want to pick 3 top areas to focus on, to protect these landscapes. Here we're not talking about protecting the individual species. We're talking about protecting the environmental setting that drives diversification. And if this has any value, then it's not just about the mammals and amphibians, but it's about all the little stuff. The snails and the insects and so on that are evolving across these same landscapes. Now that's a hypothesis to be tested. So again, Central Coast, particularly the Santa Cruz and Santa Lucia range, Central Sierra, and the transverse ranges would be my 3 top picks. Now, what we're doing isn't a totally new idea again. And in fact, Ledyard Stebbins, one of the sort of giants of evolutionary botany in California, did this sort of exercise back in the 60s with data we'd now regard as very incomplete, but it showed great vision and understanding of the plants, the 2,000-odd unique California plants. He looked at areas that had recently evolved species based on their chromosome counts, and I won't go into the details, but again, he picked out this area in the Central Coast as being an area, as well as areas in the Central Sierra, as having, again, very rapid rates of diversification in plants. And we're now getting more data to look at this. So the same theme is coming up. And this they link to both the current environmental gradients in these areas, but also the recent in evolutionary terms, evolution of the full Mediterranean type climate in California. So if we take these areas now and ask, well, what's the landscape look like? This is very preliminary. We're still pulling these data together. But one thing we did was to overlap these areas of coincident hotspots between mammals, birds, and mammals, amphibians, and in this area, the plants. and overlaid on a map of ecological integrity that Frank Davis and colleagues at UC Santa Barbara produced some years ago. The white being good, black being bad. I mean, you can tell that just glancing at the map. And there are areas that have great opportunity through collaboration between the local land trusts and TNC and state parks and the UC Reserve System and so on, to protect some of these larger scale landscapes over which evolution can operate. Other areas, as I said, are more challenging, like the Santa Cruz Ranges. Good opportunity up here. This area is already largely protected, or at least in federal lands. Much more interesting challenges down here around the LA Basin and adjacent ranges. But perhaps not hopeless. So there is something that can be done. Looking forward to how this might interact, so just because these are areas where recent evolution has occurred doesn't mean that they'll be sustainable in the longer term under climate change. And we all know climates have changed in California, and we've just started in very simplistic and heuristic fashion to ask where might these sorts of landscapes shift with climate change. And I'm not pretending this is the answer, because it doesn't even include fog and how fog is going to change. But here's sort of a cartoon version of one possibility. Here's a couple of the hotspots, Santa Cruz, Santa Lucia, with shifts in the distribution of the environmental space over which this evolution has occurred now toward the coast. But again, that all depends on what happens with the maritime fog influence. The areas like the Central Sierra, it simply disappears off the map. So these landscapes will shift, but to the extent to which they're protected on steep elevational gradients will minimize that, or at least increase the resilience of the system. To finish off, I want to move from speculation about the future to direct evidence on what past climate change has done to the distributions of these same species in California, focusing on this Central Sierra hotspot. And this is in the context of a large project underway in the Museum of Vertebrate Zoology tonight, and although nothing's been mentioned yet, but there is a reception at the museum after the conference is done today. Perhaps the organisers will say more about that. We hope as many of you can come as possible. Come and see the dead rats, the dead birds, lizards, salamanders, all the cool stuff. These collections now are 100 years old and is one of several research museums at Berkeley. And they offer a terrific record, and very detailed record of the distributions of biodiversity in California 100 years ago. So our notion, it's a very simple one, and in fact, this is way too many words, but this is a really cool paragraph. Basically, Grinnell, who set the museum up, and the benefactor, Annie Alexander, who's aiming her gun directly at Grinnell, so get it right, Joe, argued that his purpose in setting this museum up 100 years ago was so that people could come back in a century and see what's changed. That took terrific foresight in the early 20th century to think of that. But he did, and we still have the collections and all the field notes and everything that goes with it. So the collections were made all around California. We're just going to zoom in on this bit. We are also now working up here, down here, and we hope through partnerships to expand the project. But I'll show you just some initial results, and in fact, you've already had, I'll skip over that, that's where we hope you'll come. In fact, you've already got the headlines from Mark Rovshovsky. So this is the Yosemite transect, starting in the Central Valley around Snelling, up over the Yosemite National Park, outlined here, over to Mono Basin. They did it with 1,000 man days, all these field notes, specimens, photographs. We have all of those, they're all online. You can look at them yourself. We've gone back and looked at mammal distributions. Shown here is a series of elevational plots from 0 to up over 10,000 feet. Left hand being Grinnell's surveys, these being our surveys, so on and so forth. And the bottom line is that this set of species, pikers, alpine chipmunk, building ground squirrels, golden mantle squirrels, all things we know and love, heather voles, which you don't see so often, these have all moved up in their lower ranges by about 500 metres on average. That's not very subtle change. That's really dramatic stuff over 100 years. So this is an upwards contraction of the ranges, which is not good for a high elevation species. Some have had range collapses. The left one is a bushy-tailed wood rat. This is the shadow or Allen's chipmunk. They've had terrific range collapses, and this is in Yosemite National Park. So this is not due to land use change, it's in one of our conservation icons. But other things don't change. So some of the gophers, marmots, another species of chipmunk, shrews, which are high elevation specialists also, haven't changed. So there's this biological heterogeneity. We can't take one size fits all in terms of our expectations of future responses. And then, as Mark also mentioned, a couple of things, most notably the shrew, have moved down, in this case by about 1,000 metres. So highly variable responses. Some of these can be associated with fire, stand replacing fires. So we have a direct ecological cause, that's fine. But others, in fact Mark used this slide before, are much more perplexing. This is a kilometre upward shift of this pinyon juniper mouse into high elevation conifer forest. Truly astounding result. So some of the dynamics we're seeing are natural ecological dynamics, some are related to fire and normal ecological succession processes, but the big signature is one of climate change. And there's all sorts of data now emerging, still not good enough really for our purposes, but getting there, of really substantial warming in monthly minimum temperatures over the last 100 years in the Central Sierra. So this leads me to suggest, at least for us, whether it is for you as your own decision, a really urgent and emerging research priority. We have several of these historical data sets around California. I've shown you just a tiny glimpse of one of them. We have from the 20s, 30s and 40s vegetation maps and 20,000 plant plots scattered around California. Groups at Davis and Berkeley are protecting that information and digitizing it. We have this fantastic data on faunal distributions. We have, at the moment, really poor climate data on the early 20th century, which desperately needs to be improved to interpret these biological changes that we've already seen. So this definitely needs work. It is clear already that the spatial patterns of climate change in California have been really heterogeneous. Some areas have cooked, some might have even cooled a bit. And we're not going to understand how things have already responded unless we understand these spatial patterns of change in the past and in the future. So I think this is a really important exercise. I think we can make any projections we like into the future of how the vegetation and species will respond, but if we don't train those projections, if we don't test them against historical data, they will remain speculation. And I don't think you want to base billions of dollars of investment on speculation. You want solid evidence. So I think that's doable through a partnership between the state and the UC system. The other thing I'd point out is that the UC Natural Reserve System also has tremendous untapped resources in terms of long-term ecological knowledge over decades of research, and is still mostly locked up in academia. And again, as a partnership, there's the potential to bring that out and put it to work for the land trusts, for the state parks, and for the community. Thank you.
Any questions for Craig?
Thank you, Dr. Moritz. Something you said, you may not know the answer to this, but you mentioned the fog. And the fog is incredibly important in coastal California. It's why a lot of us don't need air conditioning. Has anybody studied what's going to happen to the fog? Is there going to be more of it, less of it, different times?
I'm not a climatologist. Boy, that's coming up again and again today, isn't it? Don't ask me, I'm not a climatologist. I know people are trying to produce at least good maps of the current fog influence and its current input to total precipitation, particularly in the redwood areas, because they're totally fog dependent. Where our future and past climate change models can handle fog, and it's very important contribution to total water balance. I don't know. Perhaps somebody else in the audience does. But
Where's Ruskin?
yeah, I would sure like to know the answer to that question. I think it's very important. Yeah, please.
I don't know the answer either. I'm Jane Long from Lawrence Livermore Lab, but I do know that we are looking towards trying to make more detailed models of what the climate is going to do. Most of the climate models that are used for IPCC, et cetera, are resolved on about a 200, 300 kilometer pixel size, if you want, which doesn't help tell you about the fog. So models we're developing now are down at the 6 kilometer range, and when you get down at that range, you're going to begin to see fog. And we have models that will be able to do regional climate under development that will be able to embed those in long-term trends, both in the atmospheric forcing and as well as land use issues. And that's what has to happen if we're going to understand the answer to that question. We're going to have to do those kind of studies.
Thank you.
Is there? It's on. All right. I'm very interested in your map of the biodiversity hotspots, the evolutionary hotspots, and I wonder, is there a correlation between stressors and an accelerated evolutionary pattern in some of those areas?
That's a very good question. It was, is there any connection between environmental stress and rate of evolution? Or speciation in our particular case in these systems. The sort of conceptual underpinnings of what I'm talking about sort of go back to the sort of basic ideas in evolutionary biology, and in short they are that you're more likely to evolve new forms, new species, new phenotypes in response to natural selection pushing in different directions. So environmental heterogeneity, steep gradients, and those products are more likely to survive in where there's ecological space for them to thrive. So open niche space in technical terms. So it is striking, and we're doing a formal analysis of this, but it's striking that many of the hotspots are in areas with very steep environmental gradients, areas that are geologically very active, creating new juxtapositions of communities, new landscapes, or areas that were recently deglaciated, which are also steep gradients. The sorts of environmental stress we're causing now through pollution or climate change or invasive species certainly do engender an evolutionary response, but it's unlikely, I think, that evolution is going to be able to keep up with the rate of environmental change. Migration and managing for migration responses, which has been stressed here today, I think is a much better insurance policy than one based on species overcoming climate change by evolution.
This might be, if I can interrupt for a second, this is a good opportunity. I wanted to do this today. I introduced Madeline Glickfield. Madeline is here representing the Institute of the Environment at UCLA and has something to present in relationship to evolutionary change on the human-modified environment, which gets to that question and Craig's response. So Madeline, we'll take a couple minutes to explain what it is for you to make available real soon to all of us.
Thank you. I'm really happy to be here today. I brought with me copies of a report that we just put out on the web. We're going to put out on the web in the next couple of weeks. We're going to make it available to everybody on this list. We undertook a fairly ambitious project. The Institute of the Environment is really interested in doing what we can to accelerate the movement of new science into policy and in decision making. And it is not a foregone conclusion that if you put scientists and policymakers in the same room together that you're going to get answers coming out. But you have leading edge people like we have here at Craig who are willing to answer questions that are hard questions and have their research adjusted. So we brought together evolutionary scientists from all over the world who are looking at using brand new biotechnology, are using that technology to observe in real time evolutionary changes that are occurring because of human activities. And I think that there were some conclusions that came out of that research that are talked about in the report that we're about to put out. But I think that the lessons that I have as a person who's a conservation practitioner, not a scientist, that I wanted to a couple of which I wanted to share with you are that, in fact, maintaining genetic diversity of the kind that Craig has talked about and Victoria will talk about is absolutely crucial to maintaining biodiversity in general, and that climate change, in fact, is happening too fast. What he just said is correct, that it's happening too fast for species to adapt. We're not going to be able to help species adapt unless we slow climate change. So it's going to have to be partnerships, and the kinds of things that Dr. Kammen was talking about are critically important. Things have to slow down if we have any hope of species adapting and are helping them to do so. And I think it's also important, it reflects what Craig was saying, is that a lot of people would like to see us shift all of our energies into focusing just on the climate change issue. But in fact, for biodiversity, those things that have been hurting species survival all along are actually aggravated in the sense of climate in the area of climate change. So our captive breeding programs in fishing, hunting, and the way that we deal with species in the wild, basically many times are breeding out genetic variability and reducing the ability of species to adapt to climate change. Invasive species and exotic pathogens are inhabiting large ranges of habitats. They're very versatile, and they have no natural predators, and they can become evolutionary more fit than local species. Some research that was presented at this conference says that lots of invasive exotics come in and they're latent for 5 years while they're acquiring this sounds like invasion of the body snatchers, but while they're acquiring new genetic traits, and suddenly in 5 years there's an explosion. They take over whole habitats and they're impossible to eradicate. So that says something about the importance of continuing to try to prevent the introduction of invasive species and getting at them very early. Habitat fragmentation and degradation really cuts the ability of population flow, gene flow between populations and genetic variability between species. So we can't stop doing what we have been doing. We have to continue doing what we have been doing. We have to do it better. We have to use more science to do it. And we have to also then help species to adjust to climate change. I think Craig is also right that it's going to be very hard for species to evolve in place. And so I question, and this is a question I would have asked of you, Craig, I question whether or not California is the home of endemism in the United States. And the question is, if we have such specialized climates and such specialized topography, and if there's not only just blockages of freeways and other things in urbanization, but literally we have such niche ecosystems, oughtn't we be focusing on those species and habitats that are more movable, or do we need to preserve these ecosystem niches to be able to have these in these evolutionary hotspots so that there's more adaptivity? I hope that question isn't completely unclear, but I think that there's a lot of issues about what we're doing now and what we need to change that we have to raise. Evolutionary scientists, other than people like Craig and Victoria, mainly live in their labs. They don't come out, are not observing what we're doing. So there's a huge need for us to create this connection. When I went to UCLA, I really didn't understand these issues, but I submit to you that we can't continue to do our jobs considering we are evolving species without that. Thank you.
Hello? There. Hi, Jean Panic from the Air Resources Board. I just wanted to ask a specific question about the Grinnell survey, which is this amazing resource that so many people cite because there's so few examples out there of ecological responses to physical changes, and you have something that's really well documented. It's just an amazing piece of work. So I wanted to ask about some of the reasons behind the changes that you see in the elevational shifts in the species ranges, and what kinds of insights that gives us into whether things are responding to climate change in sync, whether vegetation is moving with the species that need the vegetation, whether they eat it or they live in it or they use the shade from it or whatever. But are these things moving in sync, or are you seeing that climate change is actually creating problems in the resources that these species need?
Yeah, they're really good questions. First, thanks for your kind words about the project. It's also a lot of fun just going out and doing it. The responses we're seeing are very heterogeneous. So along with that is that communities are reorganizing. So between species that we thought interacted very closely and replaced each other, particularly in things like the chipmunks and the mice, we're also seeing it with the birds, the ecological communities are changing really drastically, particularly at high elevations. They are also, in some cases, moving ahead of vegetation change. So the pinyon juniper mouse is a classic. We thought on the east side of the Sierra that it lives in pinyon juniper woodlands. That's why it's got its name. Now it's up in whitebark pine and hemlock. So our notion of species ecological associations is usually from a snapshot in time. So I think one of the messages there that is we can't necessarily predict what the fauna is going to do on the basis of its current vegetation associations. Another message is that we certainly shouldn't be maintaining or seeking to conserve static communities. Now, any paleontologist will tell you there is no such thing as a particular species assemblage structure through time. We know from the fossil record that rodents behave idiosyncratically with past climate change, and we're seeing the same thing now over the last 100 years. So it poses a certain management challenge, a big management challenge. But one of the other things I think we're able to do now is also to spot what are the species that are resilient. So someone said before about for ecological restoration, perhaps we should be focusing on species that are going to be most resilient to future climate change. Or conversely, putting more effort into the more sensitive ones with assisted migration and what have you. We don't yet see any general principles that predict which species are resilient versus which ones are sensitive. 2 species of chipmunks are doing different things. 2 species of peromyscus are doing different things. What we can do through the study, though, is generate the information base that people can then use to design their restoration strategies, or decide, when do you have to panic about a species and which ones don't you need to panic about. I think we can get that. I think we can get that from the past changes. So that might be useful to a lot of managers out here.
One quick question and a quicker response.
Alex, the answer is no, I don't have time.
No, go ahead.
Well, actually, I was going to make a comment. So, the University of California Natural Reserve System was put together by 3 people who could be described as ecologists, Ken Norris, Bill Mayhew, and Mildred Mathias. And their principle in assembling the system initially was to get examples of all the different ecosystems of California. And of course, they focused on the fact that this is the most physiogeographically diverse state in the country. And the principle that they were pursuing was based on the fact that each of these various habitats has a different assemblage of species. So you don't find Joshua trees in the Sierra. So given that, when we talk about diversity and evolutionary rates, it's a value judgment. There's nothing absolute about it. And the state park system, for example, which is distributed throughout the state, I believe there are 272 plus sites, covers these various ecosystems. And what troubles me about focusing purely on, say, ecological drivers of evolution is that all of these habitats have physical drivers of evolution, which differ from one place to another. And whether it's species richness or species diversity that is most important. They're two different things. I mean, you can have extremes of variation. Seems to me something we can't lose sight of because we over-focus on a particular scientific choice. It may not reflect very long-term, evolutionarily most viable choices.
I think my very quick response to that would be that I agree with you that we shouldn't focus on one dimension of diversity at all. I think the more different dimensions we can look at simultaneously, the better. Whether it's functional diversity, branch lengths and phylogeny, species counts, numbers of threatened species, they're all part of the mix, but we need them all.
Okay. Thanks very much, Craig. Our next speaker doesn't spend all her time in the lab. She spent the last 4 days on the road, covered 1,200 miles sampling lichen from Washington down to Northern California, just in time for this conference. Victoria Sork is the chairperson and professor of Ecology and Evolutionary Biology Department at UCLA. She's also a professor with the Institute of the Environment at UCLA. She spent a great deal of her career studying oaks in California and has a wealth of knowledge in terms of the effects of climate change it may have on a number of oak species, but she's going to focus on valley oak today. So with that, Victoria, please come forward.
Thank you. I feel like at this point what I should be doing is telling you to all stand up and do jumping jacks because it's been a very long and stimulating day. And I have really enjoyed the range of talks and topics that we've covered. So actually, this is going to be probably one of your narrowest case studies, but I think on a very, very broad and important ecosystem to the state of California. So the only thing I didn't get here is, hang on, let me find the forward button. Okay. So before I even start, I want to point out, I'm presenting the talk, but this work represents a lot of work that's been going on for many years. Frank Davis and I have been collaborating for quite some time on Valley Oak. And this recent work that I'm going to present is from a postdoc, Delphine Grevet. Peter Smouse is a statistical geneticist from Rutgers. Bob Westphal is a forest statistician. And then I'm going to present some GIS modeling results from the geography lab at UC Santa Barbara. So I want to mention all these people because I will then go through the talk and tell you a story and forget to mention all of the people that contribute to this kind of work. Now, first of all, when you think of ecosystems in California, oaks are clearly very important. We certainly have our upper coniferous forests but the oak ecosystem is very predominant and very important to the state. Now, if you just pull all the arborescent oaks and you look at their distribution in the upper left corner, you see, yes, there's a very important ecosystem and sort of rings around the Central Valley, and you can see it going north. Quercus douglasii, this is the distribution of blue oak, and that, of course, is a little bit thicker. It's one of the more abundant ecosystems that we have, and we find it on the slopes of the foothills. Now, Quercus lobata, or valley oak, which is the one I work on, if you look at those faint light spots, it's actually been disappearing at the fastest rate of all the tree oaks in California, largely because valley oak has the misfortune of being in areas that are valuable for agriculture, valuable for wineries, and certainly a lot of urban development has been jeopardizing. So the demise of the valley oak ecosystem has been going on for about 300 years. And also I have the distribution of coastal live oak here. Now these maps I took from an article by Claudia Tyler, Bruce Mahal, and Frank Davis. But I think it's a good place to start. Now, when you think about reserve design, let me just, for a valley oak, you have to realize that it does encompass a lot of different kinds of ecosystems. So we might have this sort of oak savanna ecosystem. You also, in the upper right, you have riparian corridors where valley oak is extremely important. We have the vineyard ecosystem, which now has got an important part of the state, and valley oaks, if you have the right kind of policies, are often left behind. They're important sources of diversity for wildlife, for insects. So in terms of maintaining the connectivity, they're definitely part of the California landscape. And finally, I show you this dissected figure on the left, and I just want to point out, let's see. Okay, it's not gonna, anyway, I will go back, but it won't, okay. So if you look on the left of that dissected development, what you see is a riparian corridor. Now, what I want to point out is that agricultural development frequently has left the riparian corridors behind, whereas when we start dividing them for developments, housing projects, they frequently will completely destroy the valley oaks. So if we want to think about connectivity, the agricultural policies in the past have been a lot kinder to the valley oak riparian habitat. So here's an old picture of the distribution of valley oak. Now, when you think about how to preserve valley oak, you've got one big, huge green circle, and it's thinned out over the years. And the question is, if someone's come to me and say, where should we be preserving it? It's pretty hard as well. As long as you have some of the green, you've got valley oak. And the fact is, what I'd like to do is come up with a way of advising on how would we make choices about where to preserve valley oak. And I'm going to start the first part of my talk talking about how we can use genetic information just as markers to say, are all valley oaks created equal? And can we use genetic markers as a surrogate for identifying underlying genetic differentiation among sites? So these genetic markers are not only useful in that because these are 300 years old and it may take some time to do all of the experiments, we can get an idea of what are the differences across the state of valley oak and how could we select among them. But then it also has the advantage of now giving us evolutionary information and talking about evolutionary hotspots. So I can both use the genetic markers as surrogates for choices, and I can also use those genetic markers to talk about the evolutionary past of valley oak. Now, I want to point out, I have other research that I'm not going to present today, but I'm interested in contemporary gene flow. And we've been talking a lot about the fact that most of our best chance for things for preservation is going to be through gene movement. And of course, with things like oaks, you can get gene movement through the pollen, and you can get gene movement through the seeds. And so we have work underway to look at what is the sort of scale of contemporary movement, because we're talking about really a fast-term scale, and historical rates of movement may not be fast enough to keep track of the rates of change in the environment. And of course, here's some of the dispersal agents. These are the animals that are going to have to move these seeds around if we rely on it naturally. So let's go to this geographical genetic evolutionary approach that I want to talk about. Now, so far, the data I'll present today is on about 30 to 37 sites. We've collected more sites. I've been sort of piggybacking this project onto other funded research. So in some ways, I don't have all of the sampling that I want, but I do have enough to give you a pretty broad brush view of what's been going on. So those dots indicate the sampling sites, and then the sort of light area shows you where valley oak. So even though we haven't sampled as much as I'd like, we, for instance, haven't stratified between riparian, forest, oak woodland, that kind of ecological breakdown that eventually I think we should do. We have covered the state pretty well in terms of where we've sampled. Now, why do I distinguish between chloroplast and nuclear markers? The chloroplast is very useful in telling you the history of colonization. It's a much more conservative genetic marker. So if I want to know the history of valley oak and where things came from, the chloroplast can be very, very useful. And so they kind of tell you how much of seeds moved around. Nuclear markers Now I try to use markers that are what we call neutral, so that we can look at movement of genes as opposed to natural selection. Would be another study. So we use these microsatellites as a way of getting a sense of how much, what are the gradients, what are the underlying gradients, what are the underlying distributions of genotypes based on nuclear markers. So there are two kinds of genetic information that I can use to inform me about what does Valley Oak look like geographically. Now, I've summarized my statistical methods into a very simple slide. Anyone that would like to know how I do canonical correlation and multivariate statistics, I will be happy to tell you at question, answer, or later. But for the rest of you, like the rest of the other 101, I would just tell you simply how I do this, because it's actually very simple. What we basically do is we take a set of genetic variables, and we take a set of geographic variables, which is latitude and longitude, and I correlate them with each other. And I ask, is there any trends or correlation between the distribution of genotypes and the latitude and longitude of the state of California? Okay? So it's a pretty simple thing, but I can make it really impressive and give you a whole lecture on multivariate statistics later. So what I'm going to do is I'm going to take those variables, I'm going to correlate genes with the environment, and then I'm going to create a model and look at the trends in those data and try to project it on a map. So the question would be, is California just one big, huge Valley Oak population, or do we have areas of genetic differences that we would want to pay attention to when we do reserve design and choose where to put reserves and make sure that we've represented things? So now here is this map. I'm first going to show you the maps based on chloroplast genotypes. The light part is sort of the outline of the distribution of Valley Oak. Now, Valley Oak is not found in the Central Valley, if you remember all of those distributions I've showed you leading up to this figure. But right now, we don't have a good way to model in GIS to sort of pull out the middle, and it turns out it's not disastrous. When you see these gradients here, they're not mountains. These gradients, the dark, medium, and light, those are different kinds of genotypes. So when you go from a dark, it doesn't matter what the genotypes are, it's just telling you that the areas that are dark have the same thing, share the same genotypes. And that when you see a lot of genotypes in an area, that would tell you there's a lot of genotypic diversity over a short distance. So here is the W1 is, for those of you that know multivariate statistics, that's the first canonical axis, and W2 is the second canonical axis. But another way to think of it, it's two different views of how genotypes are distributed in California. So here, you notice in the Bay Area and in Southern California, now this is the southern part, this isn't San Diego, this is the southern part of its distribution. You get down to Thousand Oaks is where Valley Oak is its southern range. So sort of you get to the transverse ranges in that area, but on the coastal side, and then up in the Bay Area. The fact is, I highlighted those because we have sharp gradients. We have lots of different colors in a very short period of time. Probably that is due to the fact that we've got elevational gradients there. But we have elevational gradients in the eastern side of the United States, and you don't see those kind of sharp areas. So those areas both are interesting in that there's a lot of genotypic variation. There's also interesting in that one could say is that environment, the underlying heterogeneity, is generating a lot of genotypic variation. And in an interesting way, these spots, which have generated a lot of genotypic diversity, overlap with the hotspots that you're seeing for mammals and salamanders. So we're seeing some convergence in the same parts of the state between the studies. So these are high, I call these areas high genotypic because there's a lot of gradients in those colors. And here's another, and the other. When you look at the data slightly differently, we see just the whole coastal part of California is a high. By the way, we need to sample a lot more in this area. We have since I've generated these data. Let's see, okay. All right, so both of them show the coastal part of California as being important. I'm not saying that's the only thing we should preserve, but it certainly is indicating that these are places to pay attention to as we do our studies. Now, we also see, if you look and understand how to read these maps, is we have gradients of genetic differences. So if you go up and down from Southern California to north, you change shades of color, not very quickly, but what it's telling you is the genotypes you have in Southern California are different from those you have in Northern California. And that's an important point to make, because it says that big patch of green is not all equal. And you'd say, oh, duh. But the point is that we start having areas that we can say, where are there areas of difference? Where are there areas that we should sample a lot of reserves? And where are there areas, if we locate them strategically, we will be able to represent the genetic variation and the different kinds of oaks in California. So that's just based on chloroplast data. And that really gives you sort of the history, one kind of information about the structure. If I go to the nuclear genotypes, I also see similar, very, very similar areas where we have high genetic sort of gradients or difference. So these are areas of high genotypic diversity. And then here you pick up sort of an east-west gradient. In other words, with the nuclear genotypes, the individuals we're sampling in the Sierras are not the same as those that we're getting in the east. They're very different genetically. So when you put all this together, we put all this together, what you do is you see that California is really a mosaic. So now, if you just wanted to say, oh, I just want to pick up areas where there's high diversity just based on alleles with a less sophisticated analysis, each of these dots I can just represent of how diverse is each site. And we kind of just pick up overall the Bay Area, Southern California for the chloroplasts, and kind of Southern California and the Bay, but going into the Sacramento Valley for allelic diversity. So based on this sort of first pass, I could say, here are areas that we better make sure that we include as we think about reserves that we might want to sample a little more intensely. Now, how do we start thinking about reserve design in the face of climate change? I show this little cartoon for two purposes. One is to remind you the climate change we're seeing now is certainly much, much more rapid than the climate change that populations have experienced over evolutionary time. But in general, nature is, in fact, constantly switching back and forth. So that's not unusual. The other reason for showing this cartoon is just to remind you California is an unglaciated area. So in general, the whole state of California is a biodiversity hotspot, which makes it very, very valuable. Now, when we think about reserve design, I just want to acknowledge to you, I do not believe that genetics is the first thing we should go to. We have ecological criteria, geographical criteria. By that I mean we have different bioregions. We want to make sure we have state parks and UC reserves and all of these. We have areas of threat. Often we say, oh, something's going to get lost, let's save it. That's one criteria that we use. Sometimes we look at an opportunity. Someone's willing to sell something and it's not too expensive, so we just take that opportunity. What I've been focusing and what Greg Moritz is focusing is let's also think about evolutionary history when we make these decisions, because there could be important history of what's been going on in the past in California. We want to save that. And now, of course, for the symposium, we have to deal with the fact if we've got climate change. So here is some models. This is where that I got from the UC Santa Barbara lab, thanks to Lydia Rees, who'll be talking soon, and Lee Hanna and Frank Davis, et cetera. I'm putting Coast Valley Oak and Coast Live Oak right next to each other, just to point out this kind of models, these are not distribution models. These models are what's the probability that you could get a tree in this species in those areas. So they're a lot more broad brush than that. So let's look at, based on their climate models, they're using climate circulation models. They've got several versions in their work. I'm just going to show you one based on high carbon emissions. So if we take Valley Oak in the current, in 50 years, it's shifting north. And then notice in the south, we went from blue to yellow. Blue means high probability of being encountered. Yellow means marginal, and brown means very little. So let's just I don't want black. Let's back up again. Here's the current distribution. When we go forward 50 years under this particular kind of model, we see that the probability of getting, expecting to encounter, it goes north. Actually, it expands out a little bit. But in the south, we went from the blue, I can't tell, that's a dark blue, or a yellow. And now we go here, and all of a sudden, Southern California is losing out a lot. So we expect the distribution of Valley Oak to be really disappearing Now I want to show you quickly coast live oak. So of course it's along the coast. It's expanding its range, or the probability is. This says nothing about abundance, it just says probability. Now all of a sudden, interesting, you get a lot of areas all around Oregon and Nevada that suddenly say they have a high probability of they have a medium probability of being encountered. The idea that an oak is actually going to get to those places, and therefore we're going to have new ranges, we have to realize all of these models assume instant migration. So, but it gives you an idea of what could happen. And then a few years ago, Laura Cooper's published this very interesting study in Proceedings of the National Academy of Sciences, where if you look at the oak, the blue is where we're going to see them disappear, the brown is where they're going to stay, and the green. In both the blue oak on both using two, a regional climate change model and a global, both of these illustrate the shifting north, and they also point out the importance the importance of the Tehachapi's and transverse range. Okay, and so again, here are some areas of interest. Valley oak, similar story to what I was showing, which is everything is going to move up and north, except that there's going to be very critical areas like the transverse ranges, where a lot of the Southern California oaks are going to be able to go to. All right, so these are just areas of high change. So I just want to point out quickly that some of the areas that I've said are important areas of interest and important areas that are going to be sources of genetic variation after climate change are some of the areas that are most under threat for development. And the other part I want to emphasize is that most of where oaks are located are not protected forest. That green space there is forested land that's not protected. So most of oaks are distributed in unprotected lands. So this symposium today to talk about where should we acquire is quite important. And I think with that, I have a few recommendations on where, based on what I know today, I would say let's put our attention. But I should also say, I would like to see a lot more research where Frank and we start sampling in other areas and making our models a little more sensitive. And also do selective fitness experiments to actually see where seedlings are going to perform. And get a little bit of ecology to dovetail with this genetic approach. Thank you. I think everyone's...
Hi, Chris Trinnell, Conservation Strategy Group. You may not deal with this at all, but I was just wondering, what are the effects that you predict on sudden oak death coming from climate change?
Okay, so the sudden oak death, which mainly affects the coastal live oaks and several other trees, right now its distribution seems to have been cut off and not going further south than the the Santa Cruz area. I think that's largely because of dry climates. It starts getting drier and hotter. So even though it looks like sudden oak is sort of leveled out, I don't think climate change is actually going to create new habitats. If anything, it's going to reduce the habitats where it does well, at least with this pathogen the way it's behaving now.
In this case, vegetation type, and we notice, so we're kind of using this cutoff. If something is not at least 20% protected, a vegetation type, then that's considered unprotected, and that's something that we should seek out until we get everything up to that 20% level. And the last figures we had developed, maybe it was 5 years ago, was 15.5% of valley oak was in protected status. Is that match with your more recent work?
What I saw was that it's less than that. It's more like, yeah, I believe it's less than that at this point. And it's thing about valley oak, yes, it's not very little is in protected areas, and it's the most rapidly changing. This, like the San Ynez Valley is chopping up a lot of the areas. So I think it's the latest data I saw was actually less than that. Yeah.
One other question I had was on your adjusted range maps that you presented for the Valley Oak. It seemed to indicate a shift north in the range as well as a reduction. Have you quantified the reduction in its range based on those models?
Yeah, I think the work from UC Santa Barbara is still work in progress. The work that Cooper's is doing is still some of the original initial distribution. So I think we're still a little bit rough on it, but I think the message, no matter how we model it, is that the Southern California populations are really the most in jeopardy. But you know, trees live a long time, and they're very resilient, and there is potential for a lot of gene flow. So the notion of keeping some connectivity, especially along gradients, might really offer, you know, a lot of hope that if we can preserve some of the areas in California and allow some connectivity so that pollen and seeds are moving, there may be enough time for them to adjust. These trees that I'm genotyped are 350 years old, so those genes got established a long time ago, and there is a lot of genetic variation in local populations.
Thank you. Any other questions? Okay, Victoria, thank you very much. Wait, we have a little bit of time. I forgot one other thing I wanted to ask you. We got a second. Is this a good time for you to say, you feel comfortable in talking about your lichen expedition and how lichens themselves may be a strong indicator of evolutionary hotspots?
I'm going to just mention the lichens quickly because it also mentions to the fog. We have a study underway on Ramalina menziesii, the lace lichen. You all know it. It's Spanish moss, and you find it in coastal areas. It's one of the most abundant lichens in California, and everyone that's looked hangs down from the trees. And it's definitely a fog indicator. So in that sense, related to this fog discussion, it's going to be one of the first things to go as we start disrupting the fog. The reason that we picked lace lichen to add to our study, it's distributed from Baja California all the way up to Alaska. And what's interesting is there's a lot of hypotheses about different areas of evolutionary hotspots, different areas of high diversity. And the nice thing about this lichen, or the convenient thing about the lichen, is because it overlaps, it is continuously distributed. We can actually do this transect and look at regions where we have high diversity. Where does it go through genetic bottlenecks? So what our work is showing so far is that Central California, the coastal inland range, is the most diverse part of this species, and that it's more diverse than the Sierras, it's more diverse than along the coast. It absolutely overlaps with the area of highest diversity for the oaks as well. So I think this is a really very, very useful species, what we call it kind of an indicator species of where there's been glacial refugia in Western North America. And definitely Oregon and Washington, the more glaciated, its diversity goes down. But thank you.
Sounds like right where high-speed rail is proposing to go through the Pacheco Pass. Okay, we're going to take a 20-minute break and come back at, what's that, makes it 2:35. Thank you very much.